What is planet? Humanity has always been fascinated by the mysterious night sky. When we look upward at night, we see countless tiny dots scattered across the black canvas of space. Among those dots, some shine steadily while others twinkle, and a few move slowly across the heavens. For ancient civilizations, these wandering stars were objects of deep wonder, reverence, and curiosity. Today, we know them as planets. But what exactly is a planet? This question may appear simple on the surface, but its answer has evolved through centuries of human thought, observation, and scientific discovery. A planet is not just a piece of rock floating in space, nor simply a glowing point in the sky. It is a complex celestial body with distinct characteristics, histories, and mysteries that continue to inspire astronomers, scientists, and dreamers alike. The word planet itself comes from the Greek word planets, meaning wanderer. Unlike the fixed stars that appear motionless relative to each other, planets were seen to drift across the background of constellations over weeks and months. To early skywatchers, this motion made planets unique and significant. Over time, people realized that planets are not stars at all, but worlds, sometimes like Earth, sometimes vastly different, circling around the sun or other stars. With every new discovery, our definition of a planet has become more refined, more precise, and more fascinating. In modern astronomy, a planet is generally defined as a celestial body that meets three main conditions. First, it must orbit a star, like the Sun. Second, it must be massive enough for its own gravity to pull it into a nearly spherical shape. And third, it must have cleared its orbital path of other debris. This definition, adopted by the International Astronomical Union (IU) in 2006, is the most widely accepted scientific standard today. Yet even this definition has been debated, questioned, and challenged, showing that our understanding of planets is not fixed, but always evolving as we learn more about the cosmos. Planets are not only scientific subjects, they also play a profound role in our imagination and culture. Every civilization throughout history has given names, myths, and symbolic meanings to the planets they could see. Mars, the red planet, was linked to war and aggression. Venus, bright and beautiful, was tied to love and beauty. Jupiter, the largest planet in the solar system, became associated with kingship and authority. In this way, planets are not just astronomical objects, but also cultural icons that bridge science and human imagination. When we ask, what is a planet? We are not asking only about shapes, masses, orbits, and definitions. We are asking about the story of discovery, the nature of worlds beyond our own, the role of these bodies in the grand architecture of the universe, and what they mean to us as humans gazing into the night. The concept of a planet carries within it both scientific precision and poetic wonder. To truly understand what a planet is, we must explore its meaning across history, science, mythology, and the cutting-edge frontiers of space exploration. Planets vary in size, composition, and behavior. In our own solar system, we find small rocky planets like Mercury, Venus, Earth, and Mars, as well as massive gas giants like Jupiter and Saturn, and the icy worlds Uranus and Neptune. Each of these planets tells a different story about how it formed, how it evolved, and what mysteries it hides. Beyond our solar system, thousands of exoplanets have been discovered orbiting distant stars, revealing worlds that challenge our imagination. Planets hotter than fire, colder than ice, larger than Jupiter, or smaller than Earth's moon. These discoveries expand our understanding of what a planet can be, stretching the limits of our definitions and inspiring new questions about life and the universe. Therefore, answering the question, what is a planet, requires more than just a dictionary definition. It requires a journey across history, science, culture, and imagination. In the pages ahead, we will explore the origins of the concept of planets, how ancient civilizations understood them, how modern astronomy redefined them, and what mysteries still remain. We will travel through the solar system, visit each planet, and look beyond to the exoplanets of distant stars. By the end, we will see that a planet is not just a body orbiting in space, but a mirror of our own curiosity, our thirst for knowledge, and our eternal connection to the cosmos. To fully appreciate what a planet is, we must first step back into history, long before telescopes, rockets, and space observatories. Human beings have always been curious about the shining objects in the night sky, and among those objects, planets stood out as especially mysterious. Unlike stars, which seemed fixed in their positions, planets wandered slowly across the celestial sphere, sometimes brightening, sometimes dimming, and sometimes disappearing behind the sun only to reappear later. To ancient observers, this movement was not only puzzling but also deeply symbolic. The planets seemed alive, filled with purpose, and connected to the rhythms of human life. The earliest recorded observations of planets date back thousands of years to civilizations such as the Babylonians, Egyptians, Indians, Chinese, and the peoples of Mesoamerica. Each of these cultures developed unique systems of astronomy, mythology, and astrology based on their study of the planets. The Babylonians, for instance, carefully tracked the movements of Mercury, Venus, Mars, Jupiter, and Saturn, the 5 planets visible to the naked eye. They kept detailed records on clay tablets, which were later used to predict planetary positions. To them, planets were not just wandering lights, they were divine messengers, symbols of fate and cosmic order. In ancient Egypt, the movements of celestial bodies were closely tied to religious beliefs. The planets were often associated with gods and divine powers, and their positions were considered omens for the pharaoh and the kingdom. Similarly, in India, the tradition of Jyotisha, Vedic astrology, gave planets great importance. Known as grahas, the planets were seen as powerful forces influencing human destiny. Indian astronomers not only studied planetary movements, but also developed sophisticated mathematical methods to calculate their paths across the sky. Chinese astronomers also contributed enormously to our understanding of planets. They meticulously tracked planetary motions, recorded conjunctions, and even noted unusual events like retrograde motion, when a planet appears to move backward across the sky due to Earth's perspective. The Chinese often linked planets to elements such as wood, fire, earth, metal, and water, weaving together cosmology, philosophy, and observation into a grand system that guided rulers and society. The Greeks, however, were the first to attempt a systematic explanation of what planets really were. For them, the planets' wandering motion demanded a rational explanation. Philosophers like Pythagoras, Plato, and Aristotle believed that celestial objects must move in perfect circles, since circles were seen as the most perfect shape. This idea deeply influenced their models of the universe. Aristotle, in particular, placed Earth at the center of the cosmos, with planets and stars embedded in transparent spheres that rotated around us. Perhaps the most influential ancient model of planets was created by Claudius Ptolemy in the 2nd century CE. His Almagest presented a geocentric system in which Earth was stationary at the center, and the planets moved in complex paths involving circles within circles, called epicycles. While this model was mathematically complex, it successfully predicted planetary positions and dominated Western astronomy for more than 1,000 years. To people of that era, this was the truth. Planets were celestial bodies revolving around Earth in intricate orbits, reflecting a cosmic hierarchy where Earth and humanity held the central place. But the Renaissance brought a revolution. In the 16th century, Nicholas Copernicus proposed a radical new idea. The sun, not the Earth, was at the center of the universe, and the planets, including Earth, orbited around it. This heliocentric model changed everything. At first, it was met with resistance as it challenged centuries of belief and even religious doctrine. Yet it offered a simpler, more elegant explanation of planetary motion. The work of Galileo Galilei further strengthened the Copernican view. In 1609, Galileo turned his newly built telescope to the heavens and discovered astonishing things. He saw that Jupiter had moons orbiting it, proving that not everything revolved around Earth. He observed the phases of Venus, which confirmed that Venus orbited the Sun. Galileo's discovery shattered the old geocentric worldview and set the stage for a new understanding of planets as worlds in their own right. Johannes Kepler, building on the precise observations of Tycho Brahe, introduced another breakthrough. He discovered that planets do not move in perfect circles, but in ellipses, with the sun at one focus. This insight not only explained planetary motion with greater accuracy, but also introduced the laws of planetary motion, which remain cornerstones of astronomy today. Finally, Isaac Newton's law of universal gravitation provided the ultimate explanation. Planets orbit the sun because of the invisible force of gravity, which pulls them into predictable paths. Through these discoveries, planets were transformed from mystical wanderers into natural objects governed by physical laws. No longer were they divine messengers or symbols of fate alone. They were celestial bodies, subject to the same forces that shape Earth. The question of what is a planet began to take on a more scientific meaning. Planets were not just lights in the sky, but worlds, some rocky, some gaseous, some perhaps harboring life, moving through the vastness of space. The journey from ancient observation to scientific revolution reveals something essential. Our definition of a planet is not static. It grows as human knowledge grows. For early people, planets were gods. For medieval scholars, they were orbs circling Earth. For Renaissance astronomers, they were companions of the sun. And today, we see them as diverse and fascinating worlds, part of a cosmic family that extends beyond our solar system. Each stage in history has added depth to our understanding, showing that the meaning of planet is as much about humanity's perspective as it is about the objects themselves. As astronomy advanced, so did our understanding of planets. By the 20th century, telescopes had revealed more detail about the planets in our solar system, while spacecraft and probes were beginning to send back direct data. But along with these discoveries came new challenges. The more we learned about the universe, the harder it became to draw clear boundaries around what counted as a planet. For much of history, the question of what defines a planet seemed straightforward. Mercury, Venus, Earth, Mars, Jupiter, and Saturn were the classical planets, known since antiquity. Uranus was added in 1781 when William Herschel discovered it with a telescope, followed by Neptune in 1846. Then in 1930, a young astronomer named Clyde Tombaugh discovered Pluto, and it was celebrated as the ninth planet of the solar system. For decades, schoolchildren around the world learned about the 9 planets, from tiny Mercury near the Sun to distant Pluto at the edge. But as astronomers discovered more objects beyond Neptune in a region now known as the Kuiper Belt, Pluto's special status began to look uncertain. In the 1990s and early 2000s, several Kuiper Belt objects, KBOs, were found that were similar in size to Pluto. In 2005, the discovery of Eris, an object even larger than Pluto, forced the scientific community to reconsider. If Pluto was a planet, shouldn't Eris be one too? And if Eris was included, then dozens, perhaps even hundreds of other objects could also qualify. Suddenly, the solar system was not 9 planets, but potentially hundreds. This raised a critical question. What is a planet, exactly? To answer it, the International Astronomical Union, IU, the organization responsible for naming and classifying celestial bodies, convened in 2006 to establish a precise definition. After intense debate, they introduced 3 criteria that an object must meet to be considered a planet. It must orbit a star. In our case, planets must orbit the sun. This excludes moons, which orbit planets instead. It must be massive enough for its own gravity to shape it into a nearly round, spherical form. This means the object has enough mass for its gravity to overcome rigid body forces, pulling it into a balanced shape. It must have cleared the neighborhood around its orbit. In other words, a planet must dominate its orbit, either by absorbing or scattering away smaller objects so that no other bodies of comparable size share its orbital path. By this definition, Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, and Neptune were confirmed as the 8 planets of our solar system. But Pluto failed the 3rd criterion. While it orbits the sun and is round, Pluto shares its region of space with many other icy bodies in the Kuiper Belt. Therefore, Pluto was reclassified as a dwarf planet. This decision shocked the world. For generations, Pluto had been part of the cultural image of the solar system. Its demotion to dwarf planet status was seen by many as unfair or even disrespectful to the memory of its discoverer, Clyde Tombaugh. Textbooks, classroom posters, and children's songs had to be rewritten. The public reaction was emotional, with many people still refusing to accept the change. Bring Pluto Back became a rallying cry for those who felt attached to the little frozen world on the edge of the solar system. The debate over Pluto highlights something deeper. Definitions in science are not just about facts, but about perspective and agreement. Science thrives on precise classification, but the universe does not always fit neatly into human categories. Planets, moons, asteroids, and comets exist along a spectrum of shapes, sizes, and behaviors. Drawing a line between them is necessary for clarity, but it can also feel artificial. Pluto's reclassification also drew attention to a new category of celestial objects, dwarf planets. These are bodies that meet the first two criteria, orbiting the Sun and being spherical, but fail to clear their orbits. Besides Pluto and Eris, dwarf planets include Ceres in the asteroid belt, Haumea, and Makemake. Each of these worlds is fascinating in its own right, reminding us that labels like planet or dwarf planet cannot diminish the scientific importance of these objects. Moreover, the Pluto controversy sparked public interest in astronomy in a way few scientific debates ever have. For many, it served as a reminder that science is not static but dynamic, always evolving as new discoveries challenge old ideas. What we call a planet is not just a matter of tradition but of careful reasoning, evidence, and consensus. Today, the 8 official planets of the solar system form a diverse family. The 4 rocky terrestrial planets, Mercury, Venus, Earth, Mars, and the 4 gas and ice giants, Jupiter, Saturn, Uranus, Neptune. Pluto and other dwarf planets remain important members of the broader solar system, even if they do not carry the same title. The debate about Pluto also raised larger questions. Could our definition of planet change again in the future? Should exoplanets orbiting other stars be included in the same definition, or do they deserve new categories? Science is not finished with this question. In the end, Pluto's story illustrates the essence of scientific progress. A planet is not simply what we grew up learning in school. It is a concept shaped by evidence, debate, and discovery. Whether we call Pluto a planet or a dwarf planet, it remains a fascinating world with mountains of ice, possible underground oceans, and mysteries still waiting to be revealed. Labels aside, Pluto and other celestial bodies remind us of the richness and complexity of the universe, far beyond simple categories. Script on the topic: what is planet? Part 4. Once the definition of a planet was established, astronomers began to categorize planets more carefully, recognizing that not all planets are the same. In our solar system, the 8 planets fall into distinct groups based on their size, composition, and position relative to the Sun broadly. They are divided into terrestrial, rocky, planets, and giant planets. The giant planets are further separated into gas giants and ice giants. Alongside them exist dwarf planets, which add another layer of diversity. By studying these categories, we begin to appreciate not just what a planet is, but the incredible variety of worlds that exist in our cosmic neighborhood. 1. The terrestrial planets, the rocky worlds. The 4 inner planets, Mercury, Venus, Earth, and Mars, are known as terrestrial planets. The term terrestrial comes from the Latin word terra, meaning earth. These planets are small, dense, and primarily composed of rock and metal. They have solid surfaces, mountains, valleys, craters, and, in some cases, atmospheres. Mercury is the smallest planet in the solar system and the closest to the Sun. It has virtually no atmosphere, meaning temperatures swing dramatically from scorching heat during the day to freezing cold at night. Its surface is heavily cratered, resembling Earth's moon, and it orbits the Sun in just 88 Earth days. Venus, often called Earth's twin because of its similar size and mass, is actually a hostile world. It is covered with thick clouds of carbon dioxide, creating a runaway greenhouse effect that makes its surface hotter than Mercury's, despite being farther from the Sun. The surface pressure is crushing, and volcanic landscapes dominate the planet. To human eyes, Venus is both beautiful in the sky and deadly in reality. Earth, our home, is unique among planets because it hosts life. With its balanced atmosphere, abundant liquid water, and protective magnetic field, Earth is a perfect example of a habitable planet. It reminds us that planets are not just scientific objects but possible homes for life, a fact that shapes much of our search for other worlds. Mars, often called the Red Planet, has fascinated humanity for centuries. Its rusty surface, thin atmosphere, and evidence of ancient rivers and lakes make it a prime candidate in the search for past or present life. Robotic missions continue to explore Mars, preparing the way for possible human exploration in the future. Together, the terrestrial planets demonstrate how rocky worlds can vary, from airless Mercury to lush Earth to desert-like Mars. 2. The gas giants, colossal worlds. Farther from the Sun, beyond the asteroid belt, lie the gas giants, Jupiter and Saturn. These planets are massive, many times the size of Earth, and composed primarily of hydrogen and helium. Unlike terrestrial planets, they lack solid surfaces. Instead, they are dominated by thick atmospheres, deep clouds, and possibly cores of rock and metal buried under layers of compressed gas. Jupiter is the largest planet in the solar system, so massive that it could fit more than 1,300 Earths inside it. Its swirling clouds and great red spot, a gigantic storm larger than Earth, make it one of the most visually striking planets. Jupiter also has a powerful magnetic field and dozens of moons, some of which, like Europa and Ganymede, may harbor oceans beneath their icy crusts. Saturn is famous for its magnificent ring system, made of countless particles of ice and rock orbiting the planet. Like Jupiter, it is composed mostly of hydrogen and helium, with a mysterious core hidden deep inside. Saturn's moons, especially Titan, are of great interest. Titan has a thick atmosphere and lakes of liquid methane and ethane, making it one of the most Earth-like places in the solar system, though in a very different way. Gas giants remind us of the vast scales of planetary diversity. They are worlds where the rules of gravity, chemistry, and weather play out on a colossal stage. 3. The ice giants, Uranus and Neptune. Beyond Saturn lie the ice giants, Uranus and Neptune. While similar to gas giants in size, they differ in composition. Uranus and Neptune contain more ices, substances like water, ammonia, and methane, mixed with hydrogen and helium. This makes them distinct, with unique blue-green colors caused by methane in their atmospheres. Uranus is tilted dramatically on its side, with its axis of rotation almost parallel to its orbit. This unusual tilt gives it extreme seasonal variations. Its faint ring system and icy moons add to its mystery. Neptune, the farthest planet from the Sun, is a cold, windy world. It has the strongest winds in the solar system, reaching speeds of more than 2,000 kilometers per hour. Its dark storms, reminiscent of Jupiter's Great Red Spot, reveal a turbulent atmosphere. Neptune's moon Triton, which orbits in the opposite direction of Neptune's rotation, may be a captured Kuiper Belt object, linking it to the world of dwarf planets. The ice giants highlight how varied giant planets can be. Their chemistry and dynamics differ enough from Jupiter and Saturn to warrant a separate category, reminding us that even among giants, diversity reigns. Finally, there are the dwarf planets, which include Pluto, Eris, Haumea, Makemake, and Ceres, among others. These worlds are large enough to be spherical, but not dominant enough to clear their orbits. While smaller than the 8 main planets, they are far from insignificant. Ceres, located in the asteroid belt, was the first object to be discovered and classified as a dwarf planet. It has signs of water ice and possible cryovolcanic activity, making it a target of scientific interest. Pluto, once the 9th planet, continues to captivate humanity. NASA's New Horizons mission in 2015 revealed stunning details: icy mountains, nitrogen glaciers, and possible subsurface oceans. Pluto is more geologically active than anyone expected, proving that even small worlds can be complex. Eris, Haumea, and Makemake are icy bodies in the distant Kuiper Belt, each with unique characteristics. Eris is almost the same size as Pluto. Haumea is elongated due to rapid rotation, and Makemake has a bright surface covered in methane ice. Dwarf planets challenge our understanding of what a planet should be. They blur the boundaries between planets, moons, and asteroids, showing that the solar system is not neatly divided but filled with overlapping categories. In summary, the planets of the solar system are not identical but belong to distinct groups, each with unique features. From rocky Earth to gas-filled Jupiter to icy Neptune, these worlds paint a picture of diversity that is both scientifically rich and awe-inspiring. The categories of terrestrial, gas giant, ice giant, and dwarf planet help us organize our knowledge, but they also highlight the creativity of nature in shaping celestial bodies. Understanding what a planet is also requires understanding where planets come from. Like stars, planets are not eternal. They are born, they evolve, and in some cases, they may even be destroyed. The story of planetary formation is one of cosmic recycling, where matter forged in the hearts of stars becomes the building blocks of new worlds. Planets are born in stellar nurseries, vast clouds of gas and dust known as nebulae. These clouds are primarily composed of hydrogen and helium, the most abundant elements in the universe, mixed with heavier elements like carbon, oxygen, silicon, and iron. These heavier elements were created in the cores of older stars that exploded as supernovae, scattering their enriched materials across the galaxy. In this sense, planets are literally made of star stuff. When a region of a nebula collapses under its own gravity, it forms a new star. Surrounding this young star is a rotating disk of gas and dust called a protoplanetary disk. It is within this swirling disk that planets begin to take shape. The process of building planets begins at a microscopic level. Tiny dust grains collide and stick together, forming larger and larger clumps. Over time, these clumps grow into kilometer-sized bodies called planetesimals. These are the seeds of planets, and their growth is driven by both gravity and collisions. As planetesimals collide, some shatter, but others stick together, forming larger objects. Eventually, the largest planetesimals begin to dominate their region of the disk, pulling in more material through their gravity. This process, known as accretion, allows small bodies to grow into protoplanets. Not all protoplanets evolve in the same way. Their fates depend on their distance from the star and the materials available in their region of the disk. Close to the star, where it is hot, volatile substances like water and methane cannot condense. Only metals and silicate rocks can survive in solid form. As a result, the inner regions of the disk produce small, rocky planets like Mercury, Venus, Earth, and Mars. These planets are relatively small because only limited material is available. Farther from the star, where it is colder, ices like water, ammonia, and methane can solidify. Here, protoplanets can accumulate much more material, including gas. Once they reach a critical mass, their gravity becomes strong enough to attract and hold onto vast envelopes of hydrogen and helium, forming the giant planets. Jupiter and Saturn became gas giants, while Uranus and Neptune, forming slightly later or in less dense regions, ended up as ice giants with smaller gas envelopes. This distinction between rocky terrestrial planets and massive giants is a natural outcome of their birthplaces within the protoplanetary disk. As protoplanets grow, their gravity allows them to dominate their orbital zones. They sweep up or scatter away leftover planetesimals and debris, a process called clearing the neighborhood. This step is essential to becoming a true planet under the modern IU definition. Smaller bodies that fail to clear their orbits, like Ceres in the asteroid belt or Pluto in the Kuiper belt, remain as dwarf planets. The story of planetary formation is not always orderly. Planets can migrate from their birthplaces, moving closer to or farther from their stars. Interactions with a gas disk or with other forming planets can shift their orbits dramatically. Some protoplanets may be ejected entirely from the system, becoming rogue planets drifting through interstellar space. Others may collide, merging into larger planets or shattering into fragments. Evidence suggests that our own solar system may have experienced such chaotic events. For example, Many scientists believe that Earth's moon formed when a Mars-sized protoplanet, called Theia, collided with the young Earth, ejecting material that later coalesced into the moon. Similarly, Uranus's extreme tilt may be the result of a massive collision in its early history. Planet formation is a slow but powerful process. From the initial collapse of a nebula to the final clearing of orbits, it can take tens of millions of years. Yet in cosmic terms, this is a relatively short time, showing how rapidly new planetary systems can emerge around young stars. Modern astronomy provides strong evidence for these processes. Telescopes like ALMA, Atacama Large Millimeter/Submillimeter Array, have captured images of protoplanetary disks around young stars, showing gaps where new planets are likely forming. Space probes studying asteroids and comets give us direct samples of the building blocks of planets. Computer simulations reproduce the chaotic dance of collisions and migrations, giving us insight into how diverse planetary systems come into being. In this way, the story of planetary formation connects the micro and the macro, from grains of dust colliding in space to giant worlds orbiting stars. It reveals that planets are not random objects but natural outcomes of cosmic processes shaped by the laws of physics and chemistry. The formation of planets teaches us that planets are products of cosmic evolution. They are born from stardust, sculpted by gravity, collisions, and chemistry, and arranged in systems that may be stable for billions of years. This process not only explains our own solar system, but also prepares us to understand the thousands of planetary systems discovered around other stars. For centuries, humans wondered if planets existed beyond our own solar system. Were Earth, Mars, and Jupiter unique, or were there countless other worlds orbiting distant stars? Until the late 20th century, the question was purely speculative. While philosophers and writers imagined countless other Earths scattered through the cosmos, there was no direct evidence. That changed in the 1990s, when astronomers began discovering the first exoplanets, planets orbiting stars outside our solar system. Since then, the field of exoplanet research has exploded, transforming our view of planets from a handful of local examples to a vast and bewildering menagerie spread across the galaxy. The first confirmed exoplanet discovery came in 1992 when astronomers Alexander Wolszin and Dale Frail found planets orbiting a pulsar, a rapidly rotating neutron star. These planets were unexpected, tiny rocky worlds surviving in the harsh environment of a dead star's remains. While fascinating, they raised more questions than answers. In 1995, a breakthrough came with the discovery of 51 Pegasi b, the first exoplanet found orbiting a sun-like star. This planet was shocking. It was a hot Jupiter, a gas giant orbiting extremely close to its star, completing a revolution in just a few days. This defied previous theories, which assumed giant planets could only form far from their stars, like Jupiter and Saturn in our solar system. Suddenly, astronomers realized that planetary systems could be far more varied than expected. Since then, astronomers have developed several ingenious methods to detect exoplanets, even though these worlds are far too faint and small to be seen directly in most cases. The two most successful techniques are: a star and its planet both orbit a common center of mass. As the planet pulls on the star wobbles slightly. This wobble can be detected in the star's light spectrum, shifting toward red or blue as the star moves. If a planet passes in front of its star from our point of view, it causes a tiny dip in the star's brightness. By measuring these dips, astronomers can infer the planet's size, orbit, and even atmospheric composition. NASA's Kepler Space Telescope, launched in 2009, revolutionized this method, discovering thousands of planets. Other techniques include direct imaging, capturing faint light from exoplanets themselves, and gravitational microlensing, detecting planets through the bending of light caused by their gravity. Together, these methods have confirmed over 5,000 exoplanets to date, with thousands more candidates awaiting verification. One of the most astonishing outcomes of exoplanet research is the sheer variety of worlds discovered. Our solar system, once thought to be a typical example, now appears to be just one among countless possibilities. Hot Jupiters, giant gas planets orbiting very close to their stars, often hotter than molten metal. These planets defied expectations and showed that planetary migration plays a huge role in shaping systems. Super-Earths, planets larger than Earth but smaller than Neptune. Many of these have no counterparts in our solar system, yet they appear to be common throughout the galaxy. Some may be rocky, others covered in oceans or thick atmospheres. Mini-Neptunes, small gas or ice giants that straddle the line between terrestrial planets and giants. Again, our solar system has no examples, but they seem widespread elsewhere. Water worlds, planets that may be covered entirely in oceans, with no land at all. These worlds challenge our ideas of habitability and raise the possibility of alien forms of life. Rogue planets. Some planets are not bound to any star at all. Ejected during chaotic early formation, they drift through interstellar space, dark and cold, yet still counted as planets. This diversity has expanded our definition of what planets can be. No longer are they limited to the categories of rocky or giant. Instead, planets are now seen as a spectrum, shaped by a wide range of conditions and histories. Perhaps the most exciting aspect of exoplanet research is the search for habitable planets, worlds where conditions might allow liquid water and potentially life. Astronomers focus on planets in the habitable zone, the region around a star where temperatures allow water to remain liquid on a planet's surface. Kepler and other telescopes have revealed that potentially billions of Earth-like planets may exist in our galaxy alone. Some, like Kepler, 452b and TRAPPIST-1e, are particularly promising, with sizes and orbits similar to Earth's. While we do not yet know if these planets host life, their existence fuels the possibility that life may not be unique to Earth. Future missions such as the James Webb Space Telescope (JWST) and upcoming space observatories are capable of analyzing exoplanet atmospheres, searching for chemical signatures of life, such as oxygen, methane, or other biosignatures. This brings us closer than ever to answering the age-old question: are we alone in the universe? The discovery of exoplanets also raises questions about definitions. Should the IU's 2006 criteria, written specifically for our solar system, apply to exoplanets as well? For instance, the rule that a planet must orbit the Sun seems too narrow when dealing with thousands of stars. Astronomers now use a more flexible definition. A planet is a body massive enough to be rounded by gravity, smaller than a star, and formed within a stellar system. Even so, the diversity of exoplanets challenges any attempt at rigid categories. The discovery of exoplanets has changed our cosmic perspective. Planets are not rare jewels but common features of the universe. Almost every star seems to have planets, and many have systems vastly different from ours. The night sky, once imagined as fixed and unchanging, is now understood to be filled with billions of worlds, each with its own story. When we study planets through telescopes and scientific instruments, we often focus on their physical properties: mass, orbit, composition, atmosphere. But long before science could measure such things, planets were already deeply woven into the fabric of human culture and imagination. From myths and legends to astrology and art, planets have influenced how people see themselves and their place in the universe. Understanding what a planet is, therefore, isn't only about physics and astronomy, it's also about stories, symbols, and meaning. The very word planet comes from the Greek word planets, meaning wanderer. To ancient skywatchers, the stars seemed fixed in their eternal positions, but a few lights moved across the heavens in mysterious patterns. These wandering stars, what we now call Mercury, Venus, Mars, Jupiter, and Saturn, were the original planets known to humanity. Because their movements stood out, ancient civilizations gave them powerful symbolic roles. Mercury, Hermes to the Greeks, was seen as the messenger god, moving swiftly across the sky, just as the planet Mercury moves quickly around the sun. Venus, the brightest planet, was associated with love, beauty, and fertility. The Romans named it after their goddess of love, and the Greeks called it Aphrodite. Mars, with its reddish hue, was linked to blood, war, and aggression. Cultures from Babylon to Rome tied it to gods of battle. Jupiter, The largest planet visible to the naked eye, symbolized kingship, authority, and thunder. It was named after the chief Roman god, Zeus in Greek. Saturn, slow-moving and distant, represented time, harvest, and endings. It was linked to Cronus, the old god of time. To ancient people, planets weren't just lights in the sky, they were living deities shaping fate, destiny, and human affairs. From these mythological roots grew astrology, the belief that planets and their positions influence human lives. Ancient Babylonians, Egyptians, Greeks, and later cultures created elaborate systems mapping planetary movements to earthly events. Astrologers interpreted planetary alignments as signs of war, famine, prosperity, or personal destiny. For example, Jupiter's placement was thought to bring fortune and wisdom, while Mars could bring conflict. The 7 classical planets, the Sun, Moon, Mercury, Venus, Mars, Jupiter, and Saturn, formed the foundation of astrology, guiding kings' decisions and ordinary people's lives. Though modern science has shown that planets exert no mystical control over personal fate, astrology's cultural influence remains immense. Even today, millions of people read horoscopes, consult astrologers, and think about their lives in terms of planetary positions. Beyond myth and astrology, planets have been central themes in art, poetry, and storytelling. Ancient epics described gods and heroes traveling through planetary realms. Medieval and Renaissance art often depicted planetary deities as symbols of human virtues and vices. In more recent centuries, as telescopes revealed planets as real worlds, they became canvases for the imagination. Mars inspired fantasies of alien civilizations, from H.G. Wells' The War of the Worlds to Edgar Rice Burroughs' A Princess of Mars. Venus, once imagined as a lush tropical paradise, appeared in countless stories before science revealed its harsh reality. Saturn's majestic rings have inspired poetry, paintings, and even symphonies. Gustav Holst's orchestral suite The Planets remains one of the most famous musical works dedicated to planetary symbolism. Planets became not only astronomical objects but also symbols of human longing for exploration, discovery, and connection with the wider universe. Many religious traditions also wove planets into their worldviews. In Hindu cosmology, the Navagraha are 9 celestial bodies, including the 7 classical planets that influence human destiny. In Islamic astronomy, scholars studied planetary movements with mathematical precision, both for religious purposes, such as determining prayer times, and scientific curiosity. Philosophers, too, pondered the meaning of planets. Plato and Aristotle tried to explain their motions within perfect celestial spheres. Later thinkers like Giordano Bruno suggested that other planets might host life, a dangerous idea in his time, but now a mainstream scientific pursuit. Perhaps most importantly, planets have always served as mirrors of ourselves. We project onto them our hopes, fears, and values. Mars becomes a symbol of war, Venus of love, Saturn of age and death, Earth of life and home. Even as science strips away old myths, these associations linger, shaping how we interpret planetary discoveries. The story of planets is, therefore, not just about what they are but also about what they mean. They are wanderers in the sky, deities in myth, forces in astrology, muses in art, and worlds in science. They remind us that human understanding is not just measured in telescopes and equations but also in stories, beliefs, and dreams. From the very beginning of human curiosity, planets have been mysteries in the night sky. To ancient observers, they were wandering stars, lights with strange, unpredictable motions, inspiring awe, fear, and reverence. They became gods, symbols, and storytellers of fate. To astrologers, they were forces shaping human lives. To poets and artists, they were muses of beauty, war, and love. And to scientists, they became worlds, real places governed by the same physical laws that guide our own Earth. Through centuries of exploration, the meaning of planet has evolved. At first, it was a simple label for wandering lights. Later, it became a scientific category defined by size, orbit, and gravity. The International Astronomical Union even set a modern definition in 2006, sparking debates over Pluto and reminding us that language struggles to capture the universe's complexity. And then came exoplanets, thousands of them, orbiting distant stars, revealing that planets are not rare but abundant, each one a potential home for life. A planet is more than a definition. It is a world. Some are scorched by fire, others frozen in ice. Some are giants of gas and storms, others are small and rocky, perhaps with oceans, mountains, and skies. Some shine brightly in the reflected light of their stars, others drift alone in eternal darkness. Each planet is a story written in matter, gravity, and time. In the end, to ask what is a planet is to ask what it means to be human. For we are wanderers too, just like the planets. We orbit through time, searching for meaning, belonging, and knowledge. And as long as planets continue to shine above us, whether as gods in myths, destinations in space missions, or companions in the galaxy, they will remind us that the universe is vast, mysterious, and waiting to be explored. So, a planet is not just a body of rock or gas orbiting a star. A planet is a symbol of wonder. A planet is a gateway to imagination. A planet is a promise of discovery. And perhaps, one day, a planet will be our new home.